Power Integrations has been very successful with its range of InnoSwitch3-AQ automotive power conversion ICs and its family of InnoSwitch3 EP conversion ICs for appliance and industrial applications. We recently introduced the 900-volt PowiGaN technology for these families, and I'm going to spend a few minutes about why we felt the need to introduce yet another voltage technology for these product families. In order to explain why we need 900-volt PowiGaN, we need to look at the application. What I've sketched over here is a simplified version of an InnoSwitch3 power conversion IC circuit diagram for a flyback converter. Let's finish that diagram off. Now, what we have in the diagram, we have a primary clamp circuit, a flyback transformer, a primary switch, isolation barrier crossing technology, we call it flux link. Magnetoinductive coupling is the other name for it. We have a synchronous rectification on the secondary side and our outputs with a current sense, all driven by the control function built into the InnoSwitch3 IC. So in order to determine what the switching stress on the primary power switch is, we need to look at the circuit and describe how the voltage is developed across that transistor. Now, in a flyback power converter, it comes from three places. The first one's fairly obvious, what the input voltage to the circuit is. This could be VDC in an InnoSwitch3-AQ application, or something like 264√2 in a commercial or industrial application. That's the first part, so we'll call that number one. In addition, we have the output voltage reflected back to the primary. And this is controlled by the turns ratio of the power transformer. We'll call that number two. And the term for that is VOR, the voltage output reflected to the primary. The third one is the leakage energy in the power transformer. This is recycled to the primary side when the switch turns off and is controlled by the clamp circuit. And we'll call this VLE, and that'll be number three. Those three elements combine to create the voltage stress on the primary switch on the flyback converter. So let's sketch the switching waveform that we see on the power transistor when it turns off. What you get is something that looks a bit like this. So this is a DCM switching waveform. And the voltage stress on the transistor comes from those three elements. We have the leakage inductance developing the spike energy we see on the primary. So we'll call that VLE. We have the VOR, energy transferred from the secondary back to the primary, voltage reflected from the secondary back to the primary. And then we have the VDC, which is derived from the input voltage. Those three elements together are what represent the stress on the power transistor. Okay, having established that there are three elements which create the voltage stress across the primary switch, let's spend a few moments to put some values against these three parameters so we can see what the voltage rating of this switch needs to be in a typical application. So let's consider the worst case conditions in both an automotive application or an industrial and appliance application and fill in the parameter values we have here. So as you remember, we have VLE, the leakage energy from the primary clamp circuit, VOR, reflected output voltage back onto the primary, and VDC, the input voltage condition. Some of these parameters will keep the same to keep the analysis relatively simple. Let's start with VLE. Now, VLE is somewhat variable, but we'll set a typical value for an application of perhaps around 100 watts. Let's say that's going to be 70 volts. And we'll keep it the same for both a commercial application and also for an automotive design. Now let's set VOR. Again, VOR is a variable. We can control it with design parameters, but for a typical design, let's pick a value of about 150 volts. And we'll keep it the same for both again. Okay. And now let's consider the input voltage. We'll look at worst case conditions because that's what we're going to do to set the size of the voltage breakdown on our power switch. So for an industrial application, that might be 308√2, or about 430 volts. For an automotive application, we'll simply set that at 500 volts DC. Now, if we add these together, we get 650 volts. And for the automotive application, we get 720 volts. We want to add some margin onto this for a safe design. So let's add some margin. 20% derating would be nice. That would give us 130. That would be 780 volts. And this one would be 140, which would make it 860 volts. So you can see that despite the fact that the input voltage is only 400 or 500 volts, the stress on the transistor can be quite a lot higher than that. And that's one of the reasons we need to look very carefully at the voltage rating for the input switch. All right, I've cleared the board again, but I've kept the voltage value so we know what we're aiming for. Now let's look a little bit about the different technologies we have available today. If I look first of all at silicon, we have 725 volt silicon, and I'm going to use a vertical scale of voltage here. And we have 900 volt silicon. In addition, power integration's introduced 750 volt GaN. And for very high voltage applications, or for areas where we need a lot of derating, we also have available 1700 volt silicon carbide. Now, as we learned earlier, the voltage stresses we're looking for is 780 and 860 volts. So 750 volt GaN would be really good, except it's not got the voltage rating we need. 900 volt silicon would be really good, but switching losses are a little bit high at 900 volts. Also, because we have a large die size, the amount of power handling capability we can get into a 900 volt silicon transistor is a lot less than we can get into a 750 volt GaN. This is limited to perhaps 30 watts. Whereas this device can easily do more than 100 watts. So this is important, especially with some changes that are going on in the marketplace. Automotive systems are requiring more auxiliary power as the importance of the 12 volt auxiliary rail starts to decline. Industrial applications and consumer applications, commercial applications, all of these things are requiring more auxiliary power with every iteration of the products they're servicing. This means that 100 watts is much preferable to 30 watts, but we can't get more than about 30 watts into a 900 volt device. So what we've done is taken the capabilities of our 750 volt GaN and introduced a 900 volt version of that technology. 900 volt GaN gives us the switching characteristics of the 750. They're actually very close. It also allows us to fit perhaps 100 watts of power conversion capability into a standard package. And this gives us a device which gives us higher efficiency and, as noted, more power for both industrial and automotive applications. The InnoSwitch3-AQ family for automotive applications and the InnoSwitch3-EP family for appliance, consumer and industrial applications now have the benefits of 900 volt, 1700 volt and 725 volt silicon technologies. To find out more, visit us on the web at power.com.